Our next talk is titled Video Reconstruction from a Single Motion Blurred Image Using Learned Dynamic Phase Coding by Erez Yosef, Shay Elmalem, and Giryes.
Hello everyone, my name is Erez Yosef, and I will present you our work, Image and Video from Coded Motion Blur using Dynamic Phase Coding, a joint work with Shay Elmalem and Giryes from Tel Aviv University. So, motion blur. Motion blur is no limitation in photography of dynamic scenes. The exposure time is determined according to lighting conditions and noise requirements. In the acquisition, the signal is accumulated by the sensor along the motion trajectory. The main task regarding to motion blur is deblurring that aims to reconstruct a sharp image from a blurred image. Additional task is video reconstruction that aims to reconstruct sharp frame bursts of the scene from a single motion blurred image. For these tasks, both conventional imaging and computational imaging methods were suggested. And video reconstruction using conventional camera is highly ill-posed, as I will explain. Phase aperture coding is achieved using phase mask at the lens aperture. In previous works, it used for all-in-focus imaging and depth estimation from a single image. Dynamic phase coding is achieved using phase mask and focus variation during the exposure, such that we get a chromatic hues in the image, and these cues serve us as a prior information for the reconstruction process. Let's take a look at a simple example of dynamic scene. Assume we have a point light source moving from left to right. In conventional camera, we get a smear of the point such that we cannot identify the direction of the motion, if it's from left to right or from right to left. Using our dynamic phase coding, we get a coded blur such that we can know the direction of the motion. This coding is achieved using focus variation during the exposure, such that we get point spread function that changes in time. In our method, we capture a dynamic scene using our dynamic phase coding camera, and we get a coded blurred image. Using unit-shaped CNN, we reconstruct sharp frames of the video from this image. This network is dependent by time parameter that controls the reconstructed frame, such that we can reconstruct as many frames as we want, and we are not limited to specific number of frames. And the optical coding parameters are end-to-end optimized along with the network weights, as I mentioned. Okay, so let's take a look at some results. In the deblurring task, we compare our method to a conventional camera method. On the top, you can see the inputs to the networks. A, it's conventional blur using conventional camera, and B, it's our coded blur. And the reconstructions are on the bottom line and the ground truth. Although it might be hard to see on the screen, but in PSNR, our method performs better. And I will present more results in the next slide. For the video reconstruction task, we compare our method to a method by Jean et al. They use conventional camera images such that they suffer from the direction ambiguity, as I mentioned, and the method is limited for fixed number of frames. Our method is better both in PSNR and SSIM for the video reconstruction task, and all the details presented in our paper. I will not get into it right now. And let's take a look at simulation results of video reconstruction. These are the two inputs, the conventional blur and our coded blur. And these are the reconstructions. As you can see, our reconstruction is sharper and in higher frame rate. Additional simulation result, again in the same formation, These are the coded inputs. These are the blurred inputs. Our coded blur. And these are the reconstructions. Note at the textures on the tiger. Moreover, our reconstruction is in the correct direction of the motion, while the conventional camera reconstruct in the reverse direction. We built prototype camera implementing our dynamic phase coding. For the comparison, the same scenes were captured with and without the coding, and the uncoded images were processed using the conventional camera methods. For the deblurring task, we capture a dynamic scene in our lab. These are the results of the deblurring algorithms using our method and the conventional camera method. As you can see, our method succeeded to deblur the image, while the competing method didn't succeed in the deblurring task. An additional image we capture in the lab, and you can see on different sections of the image that our method reconstructs sharper images. Let's take a look at the video reconstruction results. You can see here on the left the input blurred images, and on the right the reconstructed videos. Again, you can see on the top the conventional camera suffer from direction ambiguity, such that their video is in the reverse direction. Of course, the car moving forward. And in our reconstruction, the direction is correct. Additional results for subtle motions. You can see small motions. And here, the car is placed on a base rotating to the left. And you can see the video reconstruction using our method and the conventional camera method. In our method, the motion is more homogeneous and more correct. We took also outdoor scenes. You can see the coded blurred input and the reconstructed video. Additional outdoor scene. Moreover, we extend our method for video interpolation, such that we want the input is a blurred, low frame rate video, and our construction is high frame rate, sharp video. You can see that our method is better than competing method for deblurring and frame interpolation using conventional camera. Just a second. Using our dynamic phase coding, we get more robust reconstructions, such that our method is more robust to noise, as you can see from the noise graph, compared to conventional camera methods. Additional simulation result. You can see our reconstruction compared to other conventional camera methods. And we capture video in our lab. You can see on the left the low frame rate blurred video, and on the right the reconstructed video, which is more sharp. And this is a comparison between our method and conventional camera methods. You can see also here a sharper reconstruction in our method. In conclusion, dynamic phase coding method was presented for deblurring and video reconstruction from a single motion blurred image. We presented CNN for sharp image and video recovery. We addressed the motion blurred ambiguity. And we presented a user-defined frame rate solution. And using end-to-end learning, we learned the optical coding parameters. Moreover, I showed you our video frame interpolation results using our method. Thank you very much.
Thank you, Erez. Any questions from the audience?
היי אירס, nice talk. אני ראיתי בכמה דוגמאות שלך. I saw in several examples you've shown that there is also parallax effects of the input videos or blurry frames and videos you reconstructed. So
Again,
did
sorry?
you think on another application maybe to extract disparity and depth, something like that, out of the blurry image using your coding?
The phase coding was used for depth estimation from a single image in previous works in our lab,
I see.
but not using the dynamic phase coding, namely without the focus variation during the exposure. It might be interesting to see how the dynamic phase coding can be used for depth estimation. It's something interesting to think about.
Okay, thank you very much. In the sake of time, we'll move on. Let's thank our speaker again.